Good morning, students. So today we are going to start chapter number 12, that is study of sound. Understood? So what is sound? So we can say sound is a form of energy. Sound is a form of energy which creates the sensation of hearing in our ears, right? If anyone asks what is sound, then how you will define? Then you will say sound is a form of energy which creates the sensation of hearing in our ears. Okay, this energy is in the form of wave, right? This energy in the form of wave. Understood? A medium is necessary for the propagation of sound wave. Okay, so what is the condition? What is the essential condition for propagation of a wave? The medium. Without medium, it is not possible to propagate sound. Okay, so for example, if I say just imagine you are at moon and there are two friends, and if they are talking to each other without any equipments, then you will be not able to listen what your friend is asking or what your friend is speaking, because on the surface of moon there is no medium, so you will be not able to listen what he is speaking. Okay, so medium is the essential condition for the propagation of sound. Okay, sound wave. Sound waves gives rise to a chain of compression. Sound waves gives a rise to a chain of compression. What is compression? Compression means place of higher density. Place at the place of compression there will be higher density. Okay, and rarefaction. Rarefaction means the place in the atmosphere where there is lower density is called rarefaction. In a medium, okay, in a medium, if there is higher density, then that is called compression, or if in the medium there is low density, then that is called rarefaction. The particles of the medium oscillate about their central or mean position in the direction of parallel to the propagation of the wave. Understood? Remember, I read again. The particles of the medium oscillate about their central or mean position in the direction parallel to the propagation of the wave. Actually, listen. In case of sound wave, what happened? So I am giving here examples. Suppose sound wave is moving in this direction. The direction of the propagation of sound is in this direction, and this is moving in the medium. So in the medium there will be many particles, a lot of infinite particles of the air. So in that case, suppose just imagine you are taking only one particles. Consider only one particle. There are infinite particles, but for the understanding purpose we are taking only one particles, right? So if these particles will oscillate about their mean position, it means what? Oscillate means this is the actual position, so they will oscillate in the mean position. They will come here, and again they will come back, and they will come here, and they will here. it means one oscillation completed. I repeat, these particles will displace from their mean position. It means they will come here one side, then again at the middle center position, or we can say at the mean position. Then this side they will displace maximum, and again they will come in the mean position. So we can say this is the oscillation. These particles will not move. Always remember, when sound wave is propagating, in that case particles vibrate only at their mean position, but energy particles do not travel from one place to another place. The only energy travels from one place to another place. Okay, this is very important, a very important concept. In case of propagation of wave, particles oscillate at their mean position, okay, and energy can transfer from one place to another place. So in case of sound wave, the particles oscillate in the direction of propagation of sound, okay, because this is the direction of propagation of sound wave, and this is the direction of the oscillation of the particles in the same direction, right? But in case of, there is one more wave, that is transverse wave. So in case of transverse wave, suppose wave is propagating in this direction, but medium particles will, suppose here is the medium particles. In case of transverse wave, medium particles is here. So this will oscillate perpendicular to the direction of propagation. It means what? It means wave is moving in this direction, but particles is moving perpendicular. They will, this is the mean position of the particles, so they will come they will displace this side perpendicular to the direction of propagation. They will oscillate, they will come here, and again they will come at the mean position, and again here, and again here. So you can say one oscillation completed. They will oscillate from the mean position, maximum displacement from the mean position, again they will come at the mean position, and again since this side maximum displacement from the mean position, and they will come here. It means one oscillation completed, right? So this is called transverse wave. If medium particles is vibrating perpendicular to the direction of sound wave or direction of propagation of wave, then that is called transverse wave. And if medium particles oscillates in the direction of propagation of sound wave, in that case that is called longitudinal wave. Understood? Particles oscillate wave. This one. The particles of the medium oscillate about their their central or mean position in the direction parallel to the propagation of the wave. Such waves are called longitudinal wave. This is the longitudinal wave. On the other hand, in the wave created by dropping a stone in still water, suppose you drop a stone in still water, the particles of the water oscillate up and down, up and down, up and down. These oscillations are perpendicular to the direction of propagation of the wave. Such waves are called transverse wave. So I hope you have understood these two concepts. What is longitudinal wave? So we can say, I have explained you, this is the longitudinal wave and this is the transverse wave. So the wave produced in the still water, that is example of transverse wave, and sound wave is the example of longitudinal wave. Okay. So observe and discuss. This is the medium particles. So you can say there is infinite particles in the medium. So this diagram is showing the change in density. This diagram is showing change in pressure. Okay. And this diagram is showing density or pressure. So you can see, you can easily identify this. Here is the more density, particles are very each other to each other. Particles are closer to each other. Here, and is here at the position here, and here. And here is the less density. We can say density is low because there is still particles, but they are at some distance. So this is called compression. This is called compression. This is called compression. This is compression because I have already explained you the if there is higher density in the medium, that is called compression. That is C means compression, R means rarefaction. C is compression, R is rarefaction. So there is continuous compression, rarefaction, compression, rarefaction. There is alternative compression, rarefaction, comparative rarefaction, etc. Similarly, if you consider this diagram, so you can see there is the there is higher density, there is low density, low density, low density. So this is called again compression, this is called rarefaction, compression and rarefaction. So listen, there is some different terms are there. So distance between two consecutive compression. Two consecutive means what? If you consider this compression, its consecutive will be this one. So distance between two consecutive compression or distance between two consecutive rarefaction. If you take this one, the rarefaction and rarefaction. So this is called wavelength. That is represented by lambda. Okay. So I will explain these all things later. So you can see here. This is the here is the this is the x-axis. This is the average density or pressure, and this is the density or pressure. So you can see here at the place of compression, this is the higher density, right? And at the rarefaction, you can see density or pressure is low. This is in positive and this is in negative. So we can say that where compression, this is compression. So density and pressure both are high. But in case of rarefaction, you can see this is the below x-axis, this is negative. So it means we can say that where rarefaction, if there is rarefaction, it means pressure and density both will be low, and if there is compression, then density and pressure both will be high. Understood? So I read. As a sound wave can be shown in the form of graph. At any moment during the during the propagation of a sound wave, we would find alternate bands of compression and rarefaction of the medium. That is bands of greater and lesser density. Of course, this is the high density, then less density, higher, less. This is the alternative bands. Figure 12.1 A shows the change in density, while figure B, this one B1, shows the changes in pressure. The changes in density or pressure are shown in the form of graph in the figure C. I have already explained you. Some different terms are there that I have to explain. The wavelength of sound wave is indicated by Greek letter lambda. So lambda, this symbol is used to represent wavelength, like this one. This is lambda. This is lambda. It means this is represented wavelength. While its frequency is indicated by nu. This is nu. This direction. Don't write V. So like V, like in this direct, in this way. So this is nu. This is nu. Okay. This is wrong. This is correct. The amplitude, which is the maximum value of the pressure or density, is indicated by A. Understood? So what is amplitude? The amplitude which is the maximum value of the pressure or density is indicated by A. Understood? Maximum pressure or maximum density, that is amplitude, the time taken for one oscillation of pressure or density, the time taken for one oscillation of pressure or density at a point in a medium is called time period and indicated by capital T. So what is time period? I will explain with the help of this diagram. You can take either this one or this one. So I am taking this one. So time, see, this is the compression, this is the compression. So first of all, where one oscillation completed. So if you take compression, so this distance is called this distance. If you consider compression, then this distance is called wavelength, that is represented by lambda. And you can see in this diagram, this one, this distance from this one, compression, so this is called lambda. And if you take rarefaction, if you take this distance, rarefaction, this distance will be again lambda. What is amplitude? Amplitude means higher density and higher pressure. So this one, see, this distance here, this distance, this one will be amplitude, because here is the higher density or higher pressure. Okay, this is higher pressure, this is higher density. So this is called amplitude. Maximum displacement of particles, medium particles, from their mean position. In another way you can define what is amplitude. Amplitude is the maximum displacement of particles from their mean position. In this example, suppose here is particles here, so maximum displacement either side, either this side or this side, maximum displacement from the mean position is called amplitude of the wave, that is represented by capital A. What is time period? Time period means time taken by a wave to complete one oscillation. Time taken, for example, it is better to explain you. Time taken by a wave to complete one oscillation. So one oscillation, where one oscillation is completing. Suppose this is the particles at the mean position. So maximum displacement in this side, again they will come here. They will again maximum displacement from the mean position, and again they will come here. So this is one oscillation completed. Time taken by a wave to complete one oscillation is called time period. It is represented by capital T. I hope you have understood. And what is frequency? One more term is here. What is frequency? That is nu, is represented like this, V, like this one, like this one. This is nu. So what is nu? What is frequency? So frequency, you can define frequency, number of oscillation in unit time. Number of oscillation, how many oscillations is there in unit time. Unit time means maybe we can say in 1 second, in 1 minute. So suppose there are 5 oscillations in 1 second. One oscillation completed, 2 oscillation completed, 3 oscillation completed, 4, 5. So in the number of oscillation per second is known as frequency. Okay. The value of frequency determines the pitch, high or low, of the sound, while the value of amplitude determines its strength or loudness. This is important. Frequency determines pitch, and amplitude determines strength or loudness. Research is omitted. Okay. So what is pitch? So you can define pitch is the perceptual properties of sound. What is pitch? Pitch is the perceptual property of sound. Higher the frequency, higher is the pitch. If frequency will be high, pitch will be also high. Okay. What is loudness? Loudness means simply we can say loudness refers to how much loud or soft a sound seems to be listener. Okay, how it is soft or loud for a listener. That is called loudness. Again, this is omitted. This is omitted. This has been, or this we can say, excluded in the new syllabus or reduced syllabus. Okay. So what is next? What is velocity of a sound wave? So simply the distance covered by a point on the wave in unit time is the in unit time. In unit time means we have to divide by time. Is the velocity of the sound wave. So we can see define velocity, the distance covered by a point on the wave in unit time is the velocity of sound wave. Okay, so velocity is equal to, we know that, distance upon time. Okay, so here velocity we will represent by v, and distance we will represent here lambda. In the place of distance we have to use lambda. A time is capital T, that is time period. So v is equal to lambda upon t. And one more thing, 1 upon t is known as nu. We can say this, we can write here this one, lambda upon t, we can write here 1 upon t into lambda. We can write, no problem at all, because 1 into lambda, that will be lambda, and t in the denominator, right? So 1 upon t is the frequency, that is represented by nu. That is represented by, this is not v, but you have to like this, do like this. This is nu. So in the place of 1 upon t, we can put v is equal to nu into lambda. So this is, we can also write. So nu is equal to what? Nu is the frequency. So we can say, we can write here, since nu is equal to 1 upon t. This is important. Nu is equal to 1 upon t, or simply this is not v, this is nu. This is frequency, or simply we can say this is the frequency and this is the time period. So we can say frequency here is 1, cross multiplication. If we do, then nu into t, it means frequency into time period is equal to 1. This is also, we can write this like this also. It means frequency, the product of frequency and time periods is equal to 1. Understood? So same thing is written here. So there was one questions on the first page. On the first page there is one question. Can you recall? So how does the velocity of sound depend on the frequency? So we know that v is equal to just a second, in the v is equal to, we know that nu into t. Understood? Nu into lambda. So if frequency will be high, then velocity will be also high, because both are directly proportional to each other. If velocity will be low, frequency will be also low or less. Second question is, how is the direction of oscillation of the particles of the medium related to direction of propagation of the sound wave? Right? So the medium of the particles related to in two ways. First is, medium of the particles may be parallel to the direction of propagation, and second one is, medium of the particles may be perpendicular to the direction of propagation of the sound wave. Understood? So simply velocity of sound is equal to wavelength into frequency. So you can see here velocity of the sound is equal to wavelength into frequency. That is written in the language. So one more thing, in any medium at a fixed physical condition means temperature should be same, atmosphere should be same, density should be same. In any medium at fixed physical conditions, the velocity of sound of different frequency is different, nearly the same. Nearly that will be same, but there will be difference in the same physical condition, slightly difference if physical condition is same. But if the medium change, the velocity is highest in the solid. Remember, velocity is highest in case of solid and least in gaseous. It increases with the increase in temperature. Listen, if you increase the temperature of the medium, velocity of the sound will be increase. Okay? And if you decrease the temperature, the velocity of the sound will be decrease. So you can see here, solid, the velocity of sound that is given at 25 degrees Celsius. That is almost on room temperature. Room temperature is 27 degrees Celsius. In solid, if you take aluminium, the speed of sound wave is 5420 meter per second. In case of gas, this is, you can see here, air, this is about 346. You remember this one, 346. Okay. So most maximum velocity of the sound is in solid, then liquid and finally least in the gas. Listen, velocity of sound in gaseous medium. The velocity of sound in a gaseous medium depends on the physical conditions like temperature, density of the gas and molecular weight. And I have taught you how we find the molecular weight of any compounds or any molecules. First one is temperature. So in case of temperature, you can see the velocity of the sound is directly proportional to square root of temperature. So if you increase temperature 4 times, velocity will be increased by 2 times. The reason, if you take here 4, so under root 4, that will be equal to 2. So velocity v is equal to 2. So it means if you increase the temperature 4 times, velocity of the sound will increase by 2 times. Similarly, density, the velocity of the sound is inversely proportional. Why I am saying inversely proportional? Since there is 1 upon, if something is written 1 upon something, that is inversely proportional. So in case of density, the velocity of the sound is inversely proportional to square root of density. So you can say, if you increase the density by 4 times, increase the density by 4 times, so this will be equal to v will be equal to 1 upon under root 4. So v will be equal to 1 upon 2, that is half. So you can see, in case of inversely proportional, if you increase the density of the medium by 4 times, the velocity of the sound will become half. In case of molecular weight, again velocity of the sound is inversely proportional to the molecular weight. Okay, so if you increase molecular weight by 4 times, again this will be, velocity of the sound will becomes half. So this is the homework for you. In case of oxygen gas, molecular weight is 32. In case of hydrogen, molecular weight is 2. So you have to show proof that under the same physical condition, velocity of the sound in hydrogen is 4 times. In case of hydrogen is 4 times that in oxygen. This is homework for you, and you, after solving this, you have to prove, you have to message me, or you have to send your solution on my WhatsApp number. Understood? This is the homework for you. Now next is audible, infra and ultrasound, right? So audible means if the frequency range is in between 20 hertz to 2000 hertz, then that frequency, that will be audible. We can listen. In case of infrasound, if the frequency of the sound is less than 20 hertz, so that is called infrasound. But in case of ultrasound, that is written everything. You can read here. What I am explaining, that is written here. See, if the frequency of the sound is more than 20,000 hertz, then that is called ultrasound. Remember, so same thing is written here. We listen, we can detect the sound from the frequency 20 hertz to 20,000 hertz. That is written 20, that is kilo hertz. It means kilo. If you convert kilo into simply hertz, then in the place of kilo we have to write 20 into kilo means 1000 hertz. That is 20,000 hertz. Okay. This was the uses of ultrasonic sound. So this is the omitted, but you can, if you want to read, you can read, no problem at all. This is also omitted or excluded in reduced syllabus. So now from here we have to start. Reflection of topic is reflection of sound. So light waves, sound waves too get reflected from a solid or a liquid surface, right? Like a reflection. For example, I will explain with the help of this diagram. Suppose here is a clock and here is your ear. Clock is running here. So sound will be produced from this clock. They will travel in the straight line. From this wall, reflection will be take place and they will come here. And if your ear is here, then you will be able to listen this clock. The rule is same like for the law of reflection. So we can say this in case of light, this will be incident ray, and this will be reflected ray. But in case of sound, this will be incident sound and this will be the reflected sound. This is called angle of incidence and this is called angle of reflection, right? So in case of light, we know that angle of incidence and angle of reflection both becomes equal. So in case of reflection of sound, the angle of incidence and angle of reflection both will be same, and this is the normal. So in case of sound, if you want to listen from here, then maximum sound you can hear when both the angle will be same. Understood? This is the normal. If suppose this is 45 degree and this is at 50 degree, then in that case you can listen from here, but the intensity of the sound will be decreased. When maximum sound can be when you can listen maximum sound when the angle of incidence and angle of reflection both will be equal. In that case you will be able to listen maximum sound. Okay, this wave also follow the laws of reflection. A smooth or rough listen, if this surface will be smooth, maximum reflection of the sound will take place, and if this surface is rough, then in that case least reflection of sound will be take place. So therefore we can divide this surface into two category: good reflector and bad reflector. So if this is the plain surface or smooth surface, then that is called good reflector, that will be called good reflector. And if they reflect less sound, then that is called bad reflector. Same thing is written here, you can read here. Use your brain power. This is also omitted, but if you want to do, you can. In the above activity, what will happen if you lift one of the tube to the some height? Then we cannot hear sound, or we can listen lesser sound. This one, this is talking about this one. If you lift this pipe here, so you can listen here, but the intensity of the sound will be decreased. Now, echo. You must have visited on echo point at a hill station. If you shout loudly at such a point, you hear the same sound just after a little while. This sound is called an echo. Understood? So what is echo? If you want to define echo, then you can define an echo is the repetition of original sound because of reflection by some surface. And I hope you have understood. An echo is a repetition of the original sound because of reflection by some surface. Okay. In order to able to hear the original sound and its reflection distinctly at 22 degrees Celsius, what must be the minimum distance? So what should be the minimum distance to listen echo? So here is calculation is given. So that listen, this is important. Our brain retains a sound for 0.1 second. If I say something, so that will be in your brain till 0.01 second. 0.1 second. This is very small fraction number. So if you want to calculate minimum distance, so we know that distance is equal to speed into time. So speed of the sound in the air is 344. Actually this is 346, but here is taking here is 344 meter per second. Time of retention is 0.1. So this will be equal to 34.4 meter. But this is the distance between, suppose you are here and here is some places here, and if you shout here, so this sound will go here and this will came here. So it means that the distance, if you want to calculate the minimum distance, but this is the distance from this distance to this distance. But if you want to find minimum distance for echo, then you have to divide by 2, because this is the distance between, this is the distance, minimum distance. So if you will divide this one by 2, it will get 17.2. So the condition for the echo is the minimum distance at 22 degrees Celsius is 17.2 meter. If in the classroom, generally the distance between you and the class wall is less than 17.2 meter. If in the class, if the distance between two wall is more than 17.2 meter, then even classroom we can listen an echo. Reverberation, this is omitted. So if you want to read, you can read. So this one. Sorry, only this page, students, only this page is omitted. This is omitted, but on the next page we have to study. sound waves get reflected from the walls and roof of a room multiple times. Suppose this is the singer and this is the listener, and they both are in a closed room, packed room. So in that case, if he sing anything, the listener can directly listen, or they can listen multiple times. This reflection will be take place from different surface. This is the roof. So this is the incident sound. This is the reflected sound. So again they can reflection will take place from here also. Here also multiple reflection is taking place. One time reflection from this surface. Again reflection from this surface. There are two times reflection of sound take place. Here 3 times. 1, 2, 3. So there are multiple reflection can take place inside a big room. Multiple times. This causes a single sound to be heard. Not once but continuously. This is called reverberation. It means, what is reverberation? Reverberation means the reflection, multiple reflection of sound is called reverberation. But in case of echo, there is reflection of only original. There is the reflection of repetition of original sound only. Or we can say single reflection of sound is called echo. The time between consecutive reflections of a particular sound wave reaching us becomes smaller, and the reflected sound gets mixed up to produce a continuous sound of increased loudness, which cannot be dispersed clearly. This is the reason why some auditorium or some particular seats in an auditorium have inferior sound reception. This is shown in the figure 12.3. Okay. This is also omitted. Use your brain power. This is omitted. So your next topic is sonar. This is very important. What is sonar? That is, listen, capital S, capital O, capital N, capital A, capital R. Don't write it in small letter. Sonar is the short form of sound navigation and ranging. What is the full form of sonar? This may comes in the MCQ. What is the full form of sonar? The full form of sonar is sound navigation and ranging. It is used to determine the direction, distance and speed of an underwater object. It can be used for determine the direction, distance and speed of an underwater object with the help of ultrasonic sound waves. Actually, sonar produce or generate ultrasonic wave inside the water, and due to the ultrasonic wave we can detect the direction, distance and speed of an underwater object which is inside the water. Sonar has a transmitter. This is the shape. In this shape the sonar is installed. So in the sonar there is a transmitter and there is the receiver. So transmitter transmit ultrasonic sound wave. Suppose here is an object. So from this object this incident sound will be reflect and they will reach at the receiver. This diagram is also important. This is direction. So transmitted ultrasonic sound. This is the reflected sound from the object. Okay. Transmitted pulse is here. This is the reflected pulse. The transmitter transmit ultrasonic sound waves. These waves travels through water. This wave travels through the water. Strike underwater object. Strike underwater object and get reflected by them, and they reflected by this surface. The reflected wave are received by the receiver on the ship. The reflected wave or reflected pulse is received by the receiver. This receiver, see, the receiver converts ultrasonic sound into electrical signal. This receiver converts ultrasonic sound into electrical signal, and these signals are properly interpreted. The time difference between transmission and reception is noted. The time difference between transmission and reception is noted. This time and velocity of the sound in water give the distance from the shape of the object which reflect the wave. Okay, I mean to say, if you want to find the distance between shape and the object, then what you will do? We know that distance is equal to how much? Distance is equal to velocity into time. Suppose velocity, we know the velocity of sound in water, that is how much? This is 531, but for the convenience, simple calculation we have taken 530 meter per second. Suppose 4 seconds came. It took 2 seconds. From it total time difference is 2 seconds. So we will write here 2. So this will be 3060 meter. So this is the distance between this distance and this distance. But if you want only this distance, then you have to divide by 2. So this will be equal to 1530 meter. So in this case, you can get the distance between ship and the object, right? So we can detect, so this type we detect the distance, how, if any, object inside the sea. So we can calculate, suppose you are here, this ship can calculate that how far that object is, or we can say this shape or this. So with the help of sonar technique, we can find the distance, on how much distance that object is present. So using this formula, distance is equal to velocity into time. Velocity is given. We know that the velocity of sound in the sea water, that is 530, and time, we calculate the time difference. After, suppose this transmitter sent a pulse at 8 a.m. and after 2 seconds, that is 8, after 2 seconds this received this pulses. So time difference calculated in this way. So we have to multiply by 2, but we have to find the distance only. This distance is 360, the distance between ship and the object, and object and ship. So if you will divide by 2, then you will get only this distance. So in this way we find the distance. Your next topic is sonography. So sonography technique uses, there are many applications of ultrasonic sound wave. This is very, very important. So you must read what are the uses of ultrasonic sound wave. Okay. Sonography technology uses ultrasonic sound waves to generate image of internal organs of a human body also. This is useful in finding out the cause of swelling, infection, pain, etc., the condition of the heart, the state of heart after a heart attack, as well as the growth of fetus inside womb of a pregnant woman are studied using this technique. Okay, this is only theory. This technique makes use of a probe and a gel. The gel is used to make proper contact between the skin and the probe so that full capacity of the ultrasound can be utilized. Actually, before doing sonography, they use a gel on the skin, and due to that gel, maximum amount of ultrasonic wave enters into the skin or into the body. The gel is applied on the skin outside the internal organs to be studied. Where we have to study the internal organs, where then we will use gel. First of all, we will use the gel on the skin, and after that we will put a probe on that skin so that the ultrasonic maximum capacity of the ultrasound can be utilized. High frequency ultrasound is transmitted inside the body with the help of probe. In the probe, again, there are transmitter and there are receiver. The sound reflected from the internal organ is again collected by the probe and fed to the computer, which generates the image of the internal organs. Okay, suppose this is the skin, right? First of all, we use gel on this screen, and there is a probe. In the probe, suppose this is the probe. In the probe, there is transmitter, there is receiver. So this probe we have to come here, we have to bring here, and transmitter will transmit the signal, and there will be receiver, and they will receive here. On the probe, there are transmitter as well as receiver. Transmit the signal, and due to the internal organs, they will reflect from the internal organs and receive from the receiver, and this receiver sent to the computer, and in this way we can see the internal organs on the computer. The sound reflected from the internal organs and organ is collected by the probe and fed to the computer, which generates the images of internal organs. As this method is painless, so it is increasingly used in medical practice for correct diagnosis. This is painless. There is no any pain. Always remember, this is omitted, but so you must read this one. This is very important for you. But this will not come in the paper, but you must know. Your last topic is human ear. This is the structure of human ear. So the students, you read very carefully, because on the basis of diagram, on the labeling, if suppose I will give the diagram, this diagram, and I will say label the different organs. So you must know the different name. This is auditory canal, outer ear, that is pinna, tympanic cavity, this one, chain of 3 bones is here, eardrum, this is important, this is eardrum, this vibrates, when compression comes, this go inside, when rarefaction come, they in this direction, so this vibrates. Due to the vibration, we are able to sense the sound. Okay, here is chain of 3 bones. This is the middle ear. From here to here, middle ear, and this is the inner ear. Okay. Stapes. This is the smallest bone in the ear. This is cochlea, like a snail structure. This is the inner ear. semicircular canal. This one. So you must know different name, okay? The ear is an important organ of the human body. Okay? We hear sounds because of our ear. When sound waves fall on the eardrum, I am talking about this one. This is the eardrum. It vibrates. These vibrations are converted into electrical signal which travels to the brain through nerves. Nerves convert vibration with the brain converts vibration into electrical signal. The vibrations are converted into electrical signal which travels to the brain through nerves. Nerves converts the vibration into electrical signal through the brain. Through the nerves. The ear can divide it into three parts: outer ear, middle ear, and inner ear. So outer ear or pinna. The outer ear collects the. Is it visible for you? Yes, still here it is visible for you. The outer ear collects the sound waves and passes them through a tube to a cavity in the middle ear. Outer ear collects the sounds and they passes them through a tube to a cavity in the middle ear. Its peculiar funnel-like shape. Outer ear have a peculiar funnel. This is the funnel-like shape. Helps to collect and pass sounds into middle ear. Now this diagram will be. This is not visible for you, but students, you have to manage, or you can take your textbook and you can watch observe in your textbook. Okay. Middle ear. There is a thin membrane in the cavity of the middle ear called eardrum. So where eardrum is present? Eardrum is present in the middle ear. When a compression, I have already explained you. When a compression in a sound waves reaches the eardrum, the pressure outside is increases and it gets pushed inwards. The opposite happens when rarefaction reaches there, the pressure outside decreases and the membrane gets pulled outwards. Thus, sound waves causes vibration of the membrane. So actually, when the main purpose of eardrum is to vibrate. When compression enters, they will vibrate inside, and when there is rarefaction comes, this will vibrate in outward direction. Okay, so this is the main function of the eardrum. Eardrum is, there is no any hole. So students, don't think that in the ear there is a hole. There is no any. This is all a blockage. There is no any hole. So never use any stick or anything inside the ear, because they damage eardrum. If your eardrum will be damaged, you can't hear anything. So see, there is no any hole. And don't think that there is some water came in the ear, they will go through inside the brain. No, there is no any passage. They cannot go in. They cannot enter inside the brain, because all are blockage. There is no any hole inside the ear. So this is very important. There are misconception that sometimes during bathing, water comes inside the ear. That is harmful for you. No, they will remove. No problem at all. Inner ear. The auditory nerve connects the inner ear to the brain. So which one is responsible to the brain? Auditory nerve. Auditory nerve connects the inner ear to the brain. The inner ear has a structure resembling a shell of a snail. It is called cochlea. The cochlea receives the vibration coming from the membrane and converts them into electrical signals, which are sent to the brain through the nerve. The brain analyzes these signals. Okay? This is omitted. Always remember, if you want to read, you can read. No problem at all. So this was all about your chapter number, I think 12. Study of sound. Students, numericals I will do in front of you. Otherwise, I will take. I will get time. I will take a lecture in which I will do only numericals. Okay. Till then, have a nice day. Thank you.